We begin now a study of which bases do or don't have primitive roots, beginning with prime numbers. So here's going to be the theorem we're going to prove and the first step in its proof. If p is prime, there is a primitive root mod p. In other words, there is some integer whose order mod p is phi of p. Since p is prime, that's p minus 1. The proof takes a few steps to get through. Note, if p is 2, okay, remember 2 is always kind of a special prime because it's the only even prime, then phi of 2 is equal to 1 and the order mod n of 1 is equal to 1. So 1 is a primitive root mod 2. Therefore, 2 has a primitive root. So from this point forward, we're going to assume that p is an odd prime. The first step in the proof. Suppose a and b are two integers relatively prime to n. The order mod n of a is written as j, and the order mod n of b is written as k, and furthermore assume that those two orders, j and k, are relatively prime. Then the order of a times b is j times k. So this conclusion says that the order of ab is the order of a times the order of b. This isn't always true. The assumption that those two orders are relatively prime is absolutely crucial. In general, the order of a times b is not going to be so easy to compute as the order of a times the order of b. We really need that those two orders are relatively prime. So first observe, if I take that product ab and I raise it to the jk, first step would be to call this a to the jk, b to the jk. A to the jk I'm going to write as a to the j to the k. B to the jk is b to the k to the j. A to the j was equivalent to 1 because j was the order of a. B to the k is equivalent to 1 because the order of b is k. So overall, this all works out to just be 1. All equivalences are just mod n. So jk is one particular positive power of ab that is equivalent to 1. Therefore, the order of ab must be a factor of jk. Okay, so if the order of ab is a factor of jk, and j and k were relatively prime to one another, I can write the order of AB as a factor of j times a factor of k. You can really only do this step when j and k are relatively prime. If something is a factor of a product of two numbers, you can't necessarily write it as a factor of the first times a factor of the second. We're using the fact that j and k are relatively prime. All right, so AB to its order, but its order is now written as j prime k prime. So ab to its order is equivalent to 1. I distribute that exponent on both a and b. Now x is just going to be j over j prime. Since j prime is a factor of j, this x is in fact an integer. Raise both sides to the x power. Well, on the one hand, I'd have 1 to the x. I'm just calling that 1. But then I'm going to distribute that x into both of these exponents. Now x is j over j prime. So x times j prime is just j. That, however, is the order mod n of a. So a to the j prime x k prime is a to the j prime x to the k. J prime x is j. J was the order of a. So here I just get a to its order, which is 1. So I get 1 to the k, or just 1. So this term here is just going to be 1. So 1 is equal to 1 times whatever this is. Therefore, we have found a power of b equivalent to 1 mod n. K was what we were calling the order of b. Since this is a power of b equivalent to 1, and k is the order, k must be a factor of j prime x k prime, but remember that j prime x is just j. J and k are relatively prime, so if k is a factor of j k prime, k is a factor of k prime. But remember, k prime was also a factor of k. Therefore, k and k prime are equal. Now all of this was taking this statement here and raising it to the j over j prime power. If we did all the same work, raising it to the k over k prime power, we would end up with the conclusion that j and j prime are equal. Therefore, k is k prime, j is j prime. However, we wrote the order is j prime times k, but j prime is j and k prime is k. So the order of AB is j times k, which was what we were setting out to prove. So in short, If I have the order of two different things, and those orders are relatively prime to one another, then the order of the product is the product of the orders. So let's move on to step 2, or at the very least, step 2, part A. A quick definition: an integer x is called a root mod n of a function if f of x is equivalent to 0 mod n. So this is similar to our notion of roots for real or complex valued functions, which are solutions to f of x equals 0. Here we don't require f of x to equal 0, just be equivalent to 0 mod n. So step 2-a, every element of a reduced residue system mod p is a root of the polynomial x to the p minus 1 minus 1. All we really have to do is take Euler's theorem. A to the phi of n is equivalent to 1 mod n for any a relatively prime to n. We're going to use a prime number as our base, therefore phi of n is p minus 1. Every element of a reduced residue system mod p is relatively prime to p. Therefore, x to the p minus 1 is equivalent to 1 mod p, or in other words, x to the p minus 1 minus 1 is equivalent to 0 mod p. So every element of a reduced residue system mod p is a root of that polynomial. On to step 2, part B. A polynomial over the integers is a polynomial where all the coefficients are integers. This is called Lagrange's theorem. Suppose f of x is a polynomial over the integers of degree d, and the leading coefficient is not divisible by p, which is an odd prime. Then in any reduced residue system mod p, f of x has at most d roots, where d, remember, is the degree of the polynomial. We're going to prove this by induction. For a 0-degree polynomial, we just have f of x as a constant. But since that constant has to be relatively prime to p, it's the leading coefficient, then there are no roots, because changing the value of x does not change the value of a, and a is not equivalent to 0 mod p. So for a 0-degree polynomial, there are at most 0 roots. Okay. More to the point, however, suppose d is 1. Suppose f of x is a degree 1 polynomial, so a and b are both integers. But a has to be relatively prime to p because it's the leading coefficient. B, however, doesn't, but that's fine. So any root would therefore satisfy ax plus b equivalent to 0, or ax equivalent to negative b modulo p. This has a unique solution. Since a is relatively prime to p, it has an inverse. So multiply both sides by a inverse and get x is equivalent to negative b times a inverse mod p. There's one solution. So for a degree 1 polynomial, we have at most one solution. So let's inductively assume that any polynomial over the integers of degree d whose leading coefficient is not divisible by p, there are at most d, the degree, distinct roots modulo p. Assume now to the contrary that there's a polynomial of degree d plus 1 that has d plus 2 distinct roots. So r1 through rd plus 2 are all distinct roots of this polynomial, and they're all not equivalent to each other mod p. They're actually different from each other. Well, f of r1 is equivalent to 0 because r1 is a root. So we can write f of x is equivalent to f of x minus 0. F of x would be plugging x into this polynomial. F of r1 would be plugging r1 into this polynomial. I'm now going to group terms according to what exponent I have and what coefficient I have. For example, in the polynomial, I get ax to the d plus 1, but I get a r1 to the d plus 1. So I group those two terms together and factor out the coefficient a. I would then have another coefficient x to the d and the same coefficient r1 to the d. And I would factor out the same coefficient and get x to the d minus r to the d. All the way down to the first power, I have bx minus br1, so I factor the b out. But then my constants, I just get c minus c. C minus c I can just write as 0. Now, x minus r1 I can write as x minus r1 times a 0-degree polynomial, specifically the constant 1. X to a power minus r to a power has an x minus r that can be factored out, leaving behind a degree d polynomial. This is kind of a general factoring result that, let me use different letters. If you have, let's go with s to the n minus t to the n, you can always factor an s minus t out of this, and what remains is a polynomial in s and t of lower degree. So what we're doing is, here I have the same power of x minus the same power of r1. Factor out x minus r1, and what remains is a polynomial in x of degree 1 less, so degree d. This subscript is to keep track of the degree. So from everything that I grouped together, I have 1 power of x minus the same power of this constant r1. So I factor x minus r1 out of every term, leaving behind a polynomial in x of 1 degree less. So this term gave me degree d. The next term would give me degree d minus 1, all the way down to this giving me degree 0, and then these constants just canceled out anyway. So each gi is now a polynomial over the integers of degree I. So we can actually factor the x minus r1 out of everything here. So notice what we now have is x minus r1 factored out gives me a constant times degree d polynomial. The next term would give me a constant times a degree d minus 1 polynomial, all the way down to a constant times a degree 0 polynomial, and this vanished anyway. So we have x minus r1 factored out, and now we have this big thing left over, g1 of x. This is a polynomial of degree d, or smaller, because it was g sub d plus g sub d minus 1, this sum of all these different polynomial bits, times constants, and added together. But the biggest degree I see is d, so this can't have degree larger than d. So g1 of x is a polynomial over the integers of degree at most d. However, for each of the other r's, r sub 2 through rd plus 1, f of x will be equivalent to 0. But since I assumed these were all distinct roots, x minus r1 will not be equivalent to 0. Therefore, g1 of x must be. The product of two things being equivalent to 0 modulo a prime means that the prime is a factor of the product, which means the prime is a factor of one of them. The prime base is very important here. In general, if a number is a factor of a product, it doesn't necessarily mean it's a factor of one of the two items. But for a prime, that is true. So since for each choice of r2, r3, and so forth, f of that is equivalent to 0, r2 minus r1 is not equivalent to 0, therefore g1 of r2 must be equivalent to 0. F of r3 is equivalent to 0, but r3 minus r1 is not equivalent to 0, therefore g1 of r3 must be, and so forth. So r2 all the way to rd plus 2 must all be roots of this polynomial g1. g1 was of degree d, but here are d plus 1 distinct roots. So I have a smaller degree polynomial with too many roots. We inductively assumed that any polynomial of degree d or smaller can't have that many roots. So therefore, we've proven that any integer polynomial of degree d has at most d roots modulo p, where p is a prime number. Now that we've got Lagrange's theorem behind us, we can move on to step 2, part C. More stuff about roots of polynomials. Suppose d is a factor of p minus 1. Remember, p is our odd prime. Then the polynomial x to the d minus 1 has exactly d roots mod p. Well, if d is a factor of p minus 1, let's write p minus 1 is d times k. Then x to the p minus 1 minus 1, well, p minus 1 can be written as d times k, so this is x to the dk, which is the same as x to the d to the k. Now we're going to use a factorization trick that we've used on the previous slide. Y to the k minus a constant to the k, notice 1 is the same as 1 to the k. A y minus 1 can be factored out, leaving behind all of this. Okay, now specifically, we're going to use y is equal to x to the d, because observe, I now have y to the k minus 1. Y to the k minus 1 can be factored like this. So overall, x to the p minus 1 is equal to all of this where I make this substitution. So x to the p minus 1 is x to the d minus 1 times x to the d to the k minus 1 plus x to the d to the k minus 2 plus x to the d plus 1. Now all of this in parentheses I'm just going to call f of x for simplicity, okay? So what we have is x to the p minus 1 is equal to x to the d minus 1 times f of x. Now f of x is a polynomial. What's its degree? The largest power of x is d times k minus 1. Since f of x is of degree d times k minus 1, the most roots it can have by Lagrange's theorem is d times k minus 1, or dk minus d. So f of x has at most dk minus d roots. But the polynomial on the left is just x to the p minus 1 minus 1. And step 2a established that this has exactly p minus 1, which was equal to d times k roots. So the polynomial on the left has dk roots. The polynomial on the right, f of x, has at most dk minus d roots. Therefore, the missing factor, x to the d minus 1, has at least d roots. These two things are equal, so they must have the same quantity of roots. This has exactly dk. This has at most dk minus d, so this must have at least d to make up for those missing few roots. So there are at least d roots of x to the d minus 1. But by Lagrange's theorem, again, there are at most d roots of this polynomial because it's of degree d. So since it has at least d distinct roots and also at most d distinct roots, it must have exactly d distinct roots. So the very specific polynomial x to the d minus 1 has exactly d roots provided d is a factor of p minus 1. So step 2 is behind us. On to step 3. Let p be a prime and n be a factor of phi of p. Then either there are 0 or exactly phi of n different elements that have order n. So let's try to keep track of what's what here. Okay, so let's take capital A to be a reduced residue system mod p. How many elements does a reduced residue system have? Exactly phi of p, aka p minus 1. Now the order of something has to be a factor of phi of p. So n is going to represent everything that could possibly be an order of an element. I define the set S sub n to be things in the reduced residue system whose order is exactly n. So S sub 1 is everything whose order is 1. S sub 2, everything whose order is 2. S sub 3, everything whose order is 3, and so forth. But since the order has to be a factor of phi of n, we're only letting n range over those possible choices. Then I'm going to let f of n be how many elements were in that set. So f of 1, how many things have order 1? F of 2, how many things have order 2? F of 3, how many things have order 3? And so forth. So the claim is, if f of n isn't 0, it must be exactly phi of n. Either there are 0 or phi of n different elements that have order n. How many things have order n? If not 0, then exactly phi of n. So suppose for some choice of n that f of n isn't 0. What we want to show is that f of n must be exactly phi of n. But if f of n is bigger than 0, it's at least 1. There is at least one element of order n. Let's just call that element a. Okay, so a is going to be something whose order mod p is exactly n. F of n was positive, so something has order n, we call it a. Since the order of a is n, I know if I list out all of these things, they are all distinct mod p. A to the 0 all the way to its order minus 1 will form distinct values mod p. But they are also roots of g of x is x to the n minus 1. Now why is this true? A to the I to the n, I write as a to the n to the I. But the order of a was n, so a to the n is 1. So a to the I to the n will all be equivalent to 1 mod p. So these are all distinct things that are roots of this polynomial. But g of x is x to n minus 1, where n was a factor of p minus 1. Step 2-c said this polynomial will therefore have exactly n roots. Hey, we found all of them. So the list of powers of a, from a to the 0 up to 1 shy of its order, exactly lists out the roots of this polynomial. However, any element of order n will be a root of this polynomial, because if I raise it to the nth power, I'll get out a 1 and then a 0 overall. So if something has order n, it has to be a root of this polynomial. This list exactly provides all roots of that polynomial. So anything that has order n must be in this list. However, what is the order of a to the I? It's the order of a divided by the GCD of the order of a with I. So anything of order n is in this list. Something in this list has order computed by this formula. How can it have order n if and only if the power I was relatively prime to that original order of n? In other words, I divided by a 1 here. So anything of order n is in this list. So it's a power of a. Which powers of a actually have order n? The powers that are relatively prime to n. The powers range from 0 to n minus 1. The powers that are relatively prime to n count out exactly the things that have order n. How many of these powers are relatively prime to n? Exactly phi of n of them. So overall, having found one element of order n, in other words, f of n wasn't 0, I conclude that if I call that element a, these things are all distinct mod p, but they're all roots of this. Anything of order n would also be a root of this, so anything that is of order n belongs to this list and is therefore a power of a. Powers of a can have their order computed according to this formula. So which powers of a have order n? Exactly those where the power is relatively prime to n. The powers were allowed to go from 0 to n minus 1. How many of those are relatively prime to n? Exactly phi of n. Therefore, if there was a single element of order n, there are exactly phi of n of them. Either there are no elements of order n or exactly phi of n. At long last, we can present the proof. If p is an odd prime, there is a primitive root mod p. So we're going to continue with f of n being the number of elements of order n mod p. First observation. How many elements are there in a reduced residue system mod p? There are p minus 1 of them. Each of them has an order. So if I count how many have order 1 plus how many have order 2 plus etc., I will count every element once because its order has to be somewhere in here. So every element has an order. There are p minus 1 elements, and here I count all of them once, depending on what its order is. So the sum of all of these f values must be equal to p minus 1. However, if n isn't a factor of p minus 1, there are no elements of that order. The order of any element must be a factor of phi of p, and phi of p is p minus 1. So if n is not a factor of p minus 1, then f of n is 0. There are no elements of that order. Therefore, p minus 1 isn't just this sum. I can restrict myself to only looking at the factors of phi of p. These are the only values of d for which f of d could possibly be non-zero. However, each f of d is either 0 or it's equal to phi of d. We established this in the previous slide. So I'm writing this in slightly worse way, that it's in between 0 and phi of d. But in fact, it's either one of them or the other. We also know, however, from long ago, the summatory function of the totient function is identity. So if I take the sum over factors of p minus 1 of the totient function, I'm just going to recover p minus 1. So these f of d's are either 0 or phi of d. Let's suppose that any of them are 0. Then specifically for that one term of the sum, f of d would be 0 and phi of d wouldn't, so I'd get this inequality. But then I have a contradiction. On the one hand, the sum of the values of f is p minus 1. We already established that. The sum of the values of phi is p minus 1 because the summatory function of the totient function is identity. But if any one of the terms, all of which are non-negative, satisfy this inequality, then overall the sum will satisfy this inequality, and we'll have p minus 1 is smaller than p minus 1. Well, that's not true. Therefore, I can't ever have f of d being smaller than phi of d. So f of d must equal phi of d for every possible factor of p minus 1. Specifically, phi of p minus 1 is not 0. Therefore, f of p minus 1 is not 0. Well, since f of p minus 1 isn't 0, there is something whose order is p minus 1, and p minus 1 is phi of p. So there is something whose order is phi of p. In other words, there is a primitive root mod p. So all of that work regarding roots of polynomials was really to justify the fact that the number of elements of order d is either 0 or phi of d, so that we could claim it's actually never equal to 0 as long as you're working mod p. So how many elements are there of order p minus 1? Can't be 0, has to be something, has to be a primitive root mod p.